Hello everyone. In this video we will walk through Gemma R1, a project that boosts Gemma's reasoning ability through Tunix-driven post-training. When we try to train language models in reasoning skills, some problems appear that need to be solved because training models to reason is not the same as training them to generate ordinary text. First problem. There is no single fixed training method that can always be relied on. There are multiple approaches such as supervised fine-tuning, direct preference optimization, and group relative policy optimization, and each approach has its own advantages and disadvantages and requires a different type of data design. Second problem. There is a shortage of suitable, well-structured data for training reasoning, because much of the available data does not teach the model a thinking methodology, and it does not cover a variety of realistic tasks that require steps before reaching the final answer. So, two things were necessary: building structured and diverse reasoning datasets, and then finding an approach that can practically improve the model's reasoning ability, so that it doesn't just give an answer, but follows an organized method of thinking and reaches a more accurate result. To solve the problem of choosing the right training style for reasoning, I drew this project's methodology from a simple but effective learning experience I had with my school mathematics teacher. He would start by simplifying the core idea, then solve representative examples in front of us step by step. After that, he would give us space to practice and gradually correct our mistakes until our performance improved. This sequence was translated into a multi-stage training plan using Tunix. First, supervised fine-tuning method used as the teaching and worked example stage to learn the general behavior template and how to present the solution. Second, direct preference optimization method used as the correction by comparison stage to learn a quality standard by preferring the better answer over the weaker one. Third, group relative policy optimization method used as the practice with evaluation stage, where the model generates multiple attempts and improves by rewarding outputs that meet verifiable conditions such as correctness, adherence to formatting, and the quality of the reasoning structure. In this way, the model moves step by step from learning the template to learning the quality standard, and then improving through trial and evaluation. With the training plan clarified, one fundamental question remained: what data should be used to train reasoning? Through my experience with advanced models such as ChatGPT and Gemini, I noticed an important point. Pausing to think is not necessary for every task. There are straightforward requests that a model can complete quickly, such as translation, paraphrasing, or text formatting. In contrast, there are real-world tasks that cannot be solved with a quick response because they require analyzing constraints, combining multiple pieces of information, and making a decision before writing the answer. Examples include scheduling a meeting based on several people's availability, summarizing a long meeting while extracting decisions and points of disagreement, detecting inconsistencies in a timeline, or solving a programming problem while accounting for edge cases. Therefore, when building the training data, the focus was placed on this second type of task. The examples were designed to be structured and reasoning-oriented, pushing the model to practice step-by-step thinking rather than producing polished text without logic. It was also observed that advanced models, when faced with this type of task, do not jump straight to the answer. Instead, they follow a clear pattern. They first understand the request and extract the constraints, then outline a brief plan, and finally provide the final answer. For this reason, the same approach was adopted when writing the data examples, so the model could learn a stable and consistent reasoning pattern. Now that the idea of training and proper data building has been clarified, the actual outcome can be presented. Two key changes will be noticed right away. First, the reasoning process is now structured step by step. Instead of an answer being delivered randomly or being reached through an unexplained leap, clear stages are followed. The request is understood, constraints are identified, a short plan is formed, and the solution is executed. Second, fewer mistakes are being made, and, more importantly, the question's requirements are being followed with greater precision. Rather than the response being shifted away from what is asked or being filled with unnecessary additions, the same conditions stated in the question are being respected. The required number of points, the constraints, the formatting, the time frame, and any other specific requirements. And with that, It has been shown how through structured data and a follow-up training stage using Tunix, Gemma can be moved from random outputs to clearer reasoning and more accurate answers. This is the core of the Gemma R1 project.